Hey children, welcome to the world of measurement. Previously, we have discussed about the physical quantities, non-physical quantities, and the fundamental quantities like length, mass, time, and temperature. Today, it's time for us to discuss about the fifth fundamental quantity, electric current. Before we start with electric current, we should have an idea of structure of atom, charge and its properties, insulators, conductors, and superconductors. All matter is made up of very tiny particles called as atoms. You all know matter is anything that takes up space and has mass. Atoms are the building blocks of matter, as how the bricks are the building blocks of houses. Here is the structure of an atom. An atom consists of a central nucleus. The nucleus consists of the neutrons and the protons, and the electrons revolve around the nucleus. Electrons are negatively charged, protons are positively charged, and neutrons have no charge. That is why an atom is said to be electrically neutral, because number of electrons and number of protons in an atom are equal. That is why we say that an atom is electrically neutral. So what does this word charge means? Before we go to the word charge, you should know that the electrons are very weakly held by the electrostatic force, and the neutrons and protons are held by the strongest nuclear force in the world. So it is very difficult for us to remove a proton or a neutron from the nucleus, but it is very easy for us to remove an electron. So atoms can either gain electrons or lose electrons. Atoms which are neutral, they have equal number of electrons and protons, but if an atom loses an electron, it becomes positively charged. This positively charged ion is called as a cation, and the negatively charged ion is called as an anion. And when it gets negative charge, when it gains an electron. So it is only the electron which can be either lost or gained. So what does this charge means? Charge is defined as a fundamental property of all matter. Charge is denoted by the letter Q, and the SI unit of charge is coulomb. Q here is given by the formula Q is equal to N into E, or otherwise the charge on a proton can be said as plus 1E. Here E denotes the elementary charge unit, which is the basic unit of charges, and the charge on an electron is given by the formula minus 1E. So we can say that the charges are quantized. Q is equal to N into E, where N is an integer. Its value will be positive in case of protons and its value will be negative in case of electrons. The SI unit of charge is coulomb. So charge is denoted by the letter Q. And charge is nothing but fundamental property of all matter. And charge, the SI unit is coulomb. And the value of elementary charge E is given as 1.6 into 10 to the power of minus 19 coulomb. So let us have a discussion about the properties of electric charges. You should know that like charges, they repel each other, and unlike charges, attract each other. Positive and positive repel each other, negative and negative repel each other, and negative and positive attract each other. Next property of charge is quantization of charge. That is, the net quantity or total quantity of charge present in an object is the integral multiple of elementary charge. Here, Q can be given as N into E, where N is an integer. N will be positive in terms of protons and negative in case of electrons. And the value of E can be given as 1.6 into 10 to the power of minus 19 coulomb. If the value of E is 1.6 into 10 to the power of minus 19 coulomb, then how many electrons possess 1 coulomb of charge? We can calculate that by easily a formula Q is equal to N into E. 1 coulomb is equal to N into 1.6 into 10 to the power of minus 19 coulombs. So N value can be given as 1 divided by 1.6 into 10 to the power of minus 19 coulomb. If you simplify this, you will get the value of N as 6.25 into 10 to the power of 18. So how many electrons constitute 1 coulomb of charge? 6.25 into 10 to the power of 18 electrons constitute 1 coulomb of charge. The third property of charge is conservation of electric charge. It also follows the same basic principle as the energy, conservation of energy. Electric charges can neither be created nor be destroyed. They can be transferred from one atom to the other atom. Here comes our main topic, which is electric current. You can see water current and wind current, as we study water current by the flow of water and wind current by the flow of wind. The same way, electric current is the flow of charges. So where do these charges come from? These charges, called as free electrons, are available in metals, almost all metals. Here is a cross section of a metallic wire, in which you can see that the electrons are in random motion. The free electrons, they keep on moving in a random manner here and there. They don't move in a particular direction as the students. They move in the corridor during the break time. When there is no teacher, or if they see the chairman or the correspondent, they start moving in a straight line. The same way, when this metallic wire is connected to a battery or a cell, then all the charges start flowing in a single direction and they constitute electric current. So here, negative terminal of the battery and positive terminal of the battery you can see. Okay, so here when we see that the charges flow from negative to positive, but that is the flow of electronic current. But using black arrows, they have shown the action of conventional current. So what do you mean by conventional current? Conventional current is nothing but from time immemorial, they are studying that the current always flows from a higher level to a lower level. And since positive is always taken as higher, they thought current flows from positive terminal of the battery to the negative terminal of the battery. But that is not correct. Actually, the charges, they flow from negative to positive. And this was said as electronic current. But even though now also people, they denote the flow of conventional current only in electric circuits. Here, you can say that current is nothing but the rate of flow of charges. And electric current is denoted by the letter I. I is given by intensity of electric current. I is equal to Q by T. Q here denotes the charge and T denotes the time. The SI unit of electric current is ampere. So 1 ampere of current is said to flow when 1 coulomb of charge flows in 1 second. By using this formula, I is equal to Q by T, where I denotes the current, Q is the total charge, and T is the time taken. So how can we define 1 ampere? 1 ampere is equal to 1 coulomb per 1 second. 1 ampere is defined as 1 coulomb of charge moving in a conductor in 1 second. And electric current is measured using a device called as ammeter. This ammeter is connected in series with the circuit to calculate the amount of electric current flowing through a circuit. Let us understand the formula I is equal to Q by T by solving two problems. Let us see the first problem. A charge of 75 coulomb flows through an electric heater in 30 seconds. Find the amount of electric current that flows through the circuit. Here, the value of charge Q is given as 75 coulomb. T is given as 30 seconds. By using the formula I is equal to Q by T, 75 by 30, we get the value as 2.5 amperes. Look at the second problem. A current of 0.5 ampere is drawn by an electric bulb for 5 minutes. Find the amount of electric charge that flows through the circuit. Here the amount of electric current I is given as 0.5 amperes, but the time is given as 5 minutes. Minutes is not the SI unit of time. Seconds is the SI unit of time. So we have 300 seconds. So by using the formula I is equal to Q by T, substituting the value of I and T, Q we get it as I into T. 0.5 into 300, we get it as 150 coulomb. What makes an object to conduct electricity? Let us try to understand the term conductors, superconductors and insulators. So what makes a substance conduct electricity? The presence of free electrons in a substance make it a conductor. The electrons present in insulators are strongly held by the nuclei of their atoms. So what are conductors? Conductors are the substances through which electricity can flow. And all metals are good conductors. Silver is the best conductor. Next is copper and next is aluminium. But silver, being the best conductor, is not used in electrical wires. Why? Because it's very expensive. And those substances through which electric charges cannot flow are called insulators, like glass, ebonite, rubber, plastic, paper, dry wood, etc. etc. Here are some examples of conductors. So conductors are any material that allow electric current to pass through it. Example, copper, aluminium, steel and any metal. And what is an insulator? Any material that does not allow electric current to pass through it is called as an insulator. Here you see plastic, rubber, glass, cloth, wood, everything is being used as a protective coating on metal wires so that we don't get electric shocks. So what are superconductors? Superconductors are simple conductors like superheroes, He-Man, Superman, conductors with very low resistance at very low temperature, critical temperature. We call them as superconductors. They don't allow any wastage of electrical energy in the form of heat. So how can we define superconductivity and what are superconductors? The ability of certain metals, their compounds and alloys to conduct electricity with zero resistance at very low temperatures is called as superconductivity. The materials which exhibit this property are called superconductors. Superconductors have many applications in our daily life. They are used in maglev trains. Maglev trains are nothing but magnetic levitation trains. In these trains, what they do is they have a superconductor below the train and which makes the train to float over the tracks. A superconductor, it repels the magnetic lines when cooled below the critical temperature. That is, it repels a magnet when approached towards it. So here is a maglev train without any wheels. This property is used in operating the maglev trains. Superconductors are placed below the trains and these superconductors are cooled to a very low temperature at which they will allow the maglev train to float above the tracks without any wheels. The next application of superconductor is electromagnets. Electromagnets are used in cranes. Superconductors are some of the most powerful electromagnets known. And at last, finally, superconductors can be used as memory chips in computers.